So you should see a red dot on the screen when it says recording.
It is recording.
Oh shit, we're recording. Alright, time to start. I think most of you did some progress on the Caesar and Visionaire, and at least when you broke them, you knew that you had really broken them. I mean, they're kind of self-correcting. So, I mean, when you see something which is English language and you read it out, okay, it's giving some gaps, we'll be fine. For the Visionaire, I got a bunch of questions. Oh my god, is this going to be on the exam? A, this is like the first week. B, you're not here just to learn something for the exam. And C, no. I mean, have some reason. When you're doing an exam where you don't have a computer and you will be sitting in the exam for like 2 hours doing statistics, that is not a very useful exam. On the other hand, in order to understand where crypto comes from, I want to show you some of the more historic crypto systems. One system that we didn't do yet is the column transposition. Now, that one is, your key is basically just the width of the text. And so what you do is you write the text in fixed width columns. I mean, I'm not just writing funny, this is what you're supposed to do.
Write the text in fixed width columns.
And then commute. Okay, and this permute is the second part of the key. So for instance, our key might say that we would like to have, this is the first column, this is the second column, this is the third column, this is the fourth column, this is the fifth column, and this is the sixth column. So key is the width of key plus the permutation. Oh, that's hard. Okay, and then to encrypt, you take the first column and you just copy whatever your word is in there. So ENWOTR. Second column, ITEHNPE. And there you notice already one thing which is kind of suboptimal with this system. This is certainly not the right order of these two columns. When you have text which doesn't fill up the full width, then, well, the longer columns have been on the left and the shorter columns have been on the right. Okay, now comes column 3, which is another long one. So I'll stop after this one. So RX, X, T, N, N, T, etc. So this one is a late column, and these ones are early columns. Now, again, this is something where if your width is pretty large, the number of permutations is the number of column factorial. So here we would have 6 factorial permutations. And if you do like with 100 or something, that is a lot of permutations. However, if you have a very short text, then you only have 2 columns and you have to remember the whole permutation. If you have the normal thing that like most people would find reasonable, like with 6 or something, then you can easily divide it, but it's also pretty easy to break. So it's only 6 factorial tests, and you actually have, well, whatever these 3 end up in, you can move together. You would basically, as a analyst, write them out, put them on strips of paper and move them around. If any of you is not security conscious and therefore has installed Flash Player, that's generally a bad idea. I mean, I shouldn't encourage anybody to have Flash Player, but if you have a virtual machine or something on your computer, or some old PC running prehistoric software where you really don't care about it and it still has Flash Player, we made a fun thing in Mystery Twister. It was one of the links there, where you can actually break some of these column transpositions by literally clicking on those, sliding them around. We made them so you could link them together. So if you think, oh, these two are probably in the right order because there are lots of words which have TX. No, but I mean, like, something looks like it's similar. You would again go for digraphs or something. Then you can lock them together and then slide them around in the right position. It is the nicest animation of the thing I found. Maybe I'm a little biased because I was on the team that made those challenges. But from the non-Flash Player ones, I just haven't found anything as like interactive. However, horrible Flash Player. So, and that's the old version. And it's Flash. So what you can do in that one is you can slide them around, you can ask for like digraph count of the things you move together. And so if you have any device that you don't care about anymore and you don't mind anybody having you infected with Flash, it's fine. Or you learn how to install virtual machine on your computer and sandbox it appropriately, and then it should also be fine. The last one I wanted to just comment on is a big category of rotor machines. And if you have a historical crypto course, which this one is not, but just like the introduction, there's a lot of things that cryptologists invented about rotor machines. So this is the big advancement over all of those systems, in that instead of sitting down with pen and paper and scribbling and making mistakes, you have a device. So you have basically a typewriter interface, and then of course you could take a CSR and hard code it, so when you hit A it will print out D or flip a light on D. But they were doing something cooler. They were going like, okay, we have all these problems with these fixed transpositions, even with Visionaire if there's a keyword. Now, these things work as follows. You have this typewriter interface with all the keys, and then the keystroke gets translated into something, well, rotors, hence the name of the rotor machine. So there's a whole row of rotors, and this one advances, like when you have a counter on your car, like every kilometer you advance by 1, every 10 kilometer the next one, so you have these little wheels. So this one advances at every keystroke, and this one is advances after one turn of previous wheel, of previous rotor, and then this one also advances after one turn of for its previous wheel. And then what happens is, if you push a key here, it sends a signal into here, and there's a lot of wires. such that the signal goes in here, goes in there, goes in there, goes in there, comes out somewhere else, and this one here is the ciphertext. Now, if you would hit the same letter again, the positions, the relative positions of these three rotors have changed because the rightmost one has advanced. So if you push this button again, you get a different one as your next. So this is the ciphertext for first key push. And then similar to Vigenère, so repeated keystrokes get different results. Now last year I was trying to show some demo, then one student fixed it and it's somewhat working, so you can, I'll put a link up where you can see like an online thing, but much cooler, you can actually go in the Meta forum, and we currently have an exhibition there of a bunch of rotor machines. So for instance on the 6th floor where my office is, when you're standing next to the elevator, they have some more advanced than the, say, Enigma. So Enigma is the most well-known such cipher machine because it was used in World War II, but there were a whole bunch of companies selling those until like the 70s. So go and visit, throughout the building there's a bunch of these machines. So visit the exhibit in Meta Forum. And that is a small selection of the Crypto Museum. So the Crypto Museum is a Dutch museum run by two guys who really like old crypto machines, but not just like rotor machines, they also have some more recent stuff with electronics. They don't really have regular opening hours, but one can call them and say, hey, I'm super interested, and then you can go and get a visit. We had them last year in May here at the university with an even bigger exhibition. Probably, well, I don't know whether any of you came to the Security and Time Surveillance event, which we had in May. So then they had the whole, outside the Lausaal, they had a show and tell, you could touch Enigma. Right now they're all in glass boxes. So there is cool stuff. This is on loan from the Crypto Museum. Okay, so the reason that they were much harder to break is that they had all these advanced things and they would rarely repeat. Now, they were broken mostly easily because people are stupid. That's unfortunately a case, and we still haven't advanced to that so much, but we're trying to design crypto systems so that people who don't pay so much attention don't get punished so badly. A problem here was that, say in the German military, in the Enigma, oh let me write, I should at least put this on the board, most famous example. Most famous example is Enigma in World War II. And then breaks and foremost error, but I mean there's also a lot of cool math and computer science was developed in breaking the Enigma. So one of the people who was working on the Enigma was Alan Turing, who during this time was coming up, not him alone, but there was a whole big team, but he later on then also faced the concept of the Turing machine. In the World War, they actually built some kind of computers, so it's like computers that fill a room with tubes instead of semiconductors. Bletchley Park still has a museum, and they actually rebuilt the Colossus, which is one of the gigantic machines, which was not for breaking the Enigma, it was breaking for the Tunny, so the marine cipher. And this is like an incredible noise. there's lots of physical pieces that are moving. And there is then something running through which is basically brute forcing all possibilities, and you had to manually adjust something, but it was a computer, and it was a lot faster than any human could test all of those combinations. Now these were computers, but they were single-purpose computers. There was a machine which was only built to break one cipher. Now, they had to break the cipher many times. It was not a thing that you say, hey, it's broken, and now we can lean back. The break was, they knew they could get it, but every day or every time the settings were changed, they had to start from scratch. Now, what are the settings on such a machine? So on those things, the day setting is A, which wheels do you put in, and what is the starting position. For the Enigma in particular, there was another piece which was a plucker board, so a piece where you could reroute electricity coming out here. So you had like long cables, you could, short cables you could plug in here, and you could connect these. So the settings of the day were basically the rotors and which ones are connected. Which rotors, what position, and plugs, at least for the Enigma. And then when I say humans messed up, is they start sending something, at that point they go for the beginning of the day. Now, the Allies would intercept this because it's like sent by radio. And then the other end goes like, we're not so sure, maybe something went wrong. I mean, you must have noticed when you're doing by hand calculations for the last exercise, sometimes things go wrong. All right, so they call in pretext to the station which had sent the ciphertext saying, we have a problem, could you retransmit? Okay, so then they go and retransmit by putting everything to the original position. So then you get two encryptions. Now if they were doing exactly the same plaintext under exactly the same settings, you would get the right thing. But probably they vary somewhere. Like, they change the time. Like, they keep the same whatever Heil Hitler and shit, but they change the time when it's sent. So you have lots of pieces that are identical, then you have some differences, and you can correlate those. And that tells you something more what happened. Or you have some people who just forgot that their body this morning had already reset it, and then sent two messages with the same initial settings that are not correlated. And then also there were some header fields. So header is like an email, the subject line and whatever, and also army letters normally have headers. So who sends it, to whom, to what, and then 3 letters that say something about, okay, do we have the right settings? And so when you're spying on those and you notice, oh, there's a lot of similarities except for those things don't match, then you also have a good idea that there's some repetitions. And those were the things that they used in order to massively speed up the brute force. So this gigantic Colossus machine is starting from good guesses. It's not doing a brute force throughout the whole key space, it's doing some intelligent brute force. And so, I don't know how many of you tried Visionaire by doing their own implementation, when you're searching for like repeated combinations of letters. There were those things also in the ancient, well, not so ancient, like less than 100 years ago. So in the, still we call this classical crypto because it is before we started having a lot of math in there. Okay. Nowadays, the number of combinations is small enough, you could actually brute force it without having anything intelligent. But it's actually, compared to the Visionaire and such, these rotor machines did manage to get a huge amplification in the key space. So, errors were repeating initial position with different plaintext. Now, one thing which you already saw on the exercise sheet was the Hill cipher. So I'm not going to do the description here because you just saw it. So this is, again, going for more math. I mean, you also said that the Caesar cipher you can describe in math by saying, okay, it's an addition mod 26. But the Hill cipher is using more of that. It's combining the pieces. And the way that you could break it in the second exercise, you actually had a plaintext-ciphertext pair. And you had, well, not just one, you had 2 ciphertext pairs, so you could write 4 linear equations in the 4 unknowns that you have. Could I get a show of hands of who solved the last part? Like, who thinks he has a matrix that translates those two? That is not the majority. Okay, let's start doing this a little bit. And you all need to help me because I'm on the blackboard, I'm going to make mistakes. So the last part of exercise says, okay, we have some matrix M, and we multiply it by T transpose, and we get the ciphertext transpose. Alright, so our matrix now has 4 entries. Let's call them R, S, T, and U. And we know that we multiplied it by, what do I multiply by? What's the first vector? 1, 3?
3.
And I get
-9, -2.
-9, -2. And the second one is same system, R, S, T, U times
7 and 2.
7 and 2. And I'm getting -2, 9.
-2 and 9.
Super randomly chosen, of course. I'm not going to show you how to do the full thing. We're going to do R and S, and if you understand how to get R and S, you can also do T and U. What we see here is, I know that R times 1 plus S times 3 is -9. So let me write this here. 1 times R plus 3 times S is -9. And the other equation I have about R and S is that 7 times R plus 2 times S is -2. So here we have a system of 2 linear equations and 2 variables. It's actually very nice in attacking the Hill cipher that it's not like a 4x4 matrix that you're solving. It's actually 2 times a 2x2 matrix, which is a little nice. Alright, so if I want to solve these guys, then I take the first equation times -7 and multiply on this one. Add to this one. So plus times -7. We add those and take times -7. Okay, then the first part goes away. And then for the S, I have -21 times S, -21 plus 2 times S. Okay, that is -19. And mod 26, that is 7. Am I still right? Yes?
Yeah.
That is like, also this is 5 plus 2 is 7. Okay, on this side, that is 63 minus 2 is 61. There should be congruences everywhere. Now 61 is 9 more than 52, so that's going to 9 mod 26. Okay, so far I think most of you still got. I mean, at least if you got to the last exercise, I assume you got this far. And then I saw some fractions on sheets. And of course it's very, very tempting to say S is 9/7. But 9/7 is not a valid entry in the integers once again. So we need to find inverse of 7, so 7 to the minus 1, mod 26. Okay. I could take all numbers between 0 and 25 and figure out whether they're just one larger than 26. For some numbers that's fine. Say if I'm asked to invert 3, then I know 3 times 9 is 27, so that was easy. But if I want to do this with 7, that's not fun. You could try, but the reason I put this on the exercise sheet is actually to remind you of the extended Euclidean algorithm. So this needs the extended Euclidean algorithm. So that's the, normally I will just say it uses X GCD. So GCD because it's a computation of the greatest common divisor, and X because it's the extended version. Now, in principle, if you're sitting here, you should have seen either your math student, and you have seen the extended Euclidean algorithm more times than you could count. Okay, your mathematician can count for a long time, so many, many times. And probably also fairly recently in lectures in the algorithmic number theory course, so the 2WF80, no 70. If you're a computer scientist and following the whole package, then you should have taken the algebra for security, that's the 2WF90, where you also have seen this one again. And then those of you who can't read instructions or decided to come here anyway, all right, let's give you a little bit of a chance, but you will need to do some reading. So, the XGCD, this takes two numbers, A and B, in the integers, and computes the greatest common divisor. So that means the GCD of A and B, and gives a linear combination of A and B summing up to this GCD. So it computes it and gives that the GCD of A and B is some X times A plus some Y times B for, well, the X and Y, so with X and Y in Z, and more importantly, that X is smaller than B and Y is smaller than A in absolute value. What does this have to do with inversion? So if you want to compute A mod B, so to compute, A inverse to make this possible at all, I mean for this thing to exist, the GCD must be 1. So to compute, it needs to exist. And that means that the GCD of A and B is 1. Okay, and then we get x and y with this property. So this one we know already getting in. So but the cool thing is, if we know that 1 is equal to x times a plus y times b, and we're now computing this thing mod b. Okay? Then 1 stays 1. We'll get a congruence instead of an equality sign. I don't know anything about x and a. Well, we start with them being reduced mod b. I mean, a is some number less than b. And here we see that x is an absolute value less than b. So no reduction there because we actually want to keep a as an integer. So each of them doesn't get reduced. And here we have 0. So plus y times 0 is just x times a mod b. So that means we have 1 is equal to x times a. Well, a inverse, multiply by a inverse, then we get a times a inverse, it goes away here. So we have a inverse equals x. So a to the minus 1 is congruent to x mod b. Okay, are you now excited and want to learn how the XGCD works? Okay, those of you who solved this thing, you already know that. Those of you who didn't get this far because you were stuck in Visionaire and go like, yeah, whatever. But those of you who didn't get here for whatever reason and maybe have forgotten since 3 weeks ago how it worked, here's a short one. So this is, we'll have that every row satisfies that the first entry of the row is equal to, which we're going to write it, b is the bigger one, so the second entry of the row times b plus the third entry of the row times a. So we start very easily. We write b is 1 times b plus 0 times a. Another row with a, that's 0 times b and 1 times a. We will want to end up with 1 is y times b plus x times a. And that's the x we will want. Now we put here the division of b divided by a, rounded down. So that's going to be our quotient 1. And then we put here row 1 minus q1 times row 2. So we're getting b minus q1, that's the fraction here, times a. Now q1 is almost b divided by a. So this is very close to b minus b over a times a, so b minus b is 0. So this thing is getting smaller. But since we're doing the floor here, so we're rounding down, there usually is some left over. Well, there definitely is some left over, else the GCD wouldn't be 1. And then here we have 1 minus q times 0, so that's 1. And here we have 0 minus q1 times 1, so that's minus q1. Okay, so then we take this thing as a new second row, and this is the first row. So we now have next fraction a divided by whatever is here, in this case b minus q1 times a, and that we call q2. And then we do the same. So what we get here is row 2 minus q2 times row 3. And we do this till the R1 is 1. Now in our case, we wanted to invert 7 mod 26. So our example has 26 is B, we're writing 1, 0, 7 is A, we're writing 0, 1. Now 7 fits in 26 3 times, it's 21, so that's a quotient. Now 26 minus 3 times 7, so 26 minus 21 is 5. 1 minus whatever, 0, and here we get a minus 3. Next step, 7 divided by 5 is 1 comma something, so let's round it out to 1. 7 minus 1 times 5 is 2. 1 minus minus 1 is minus 1. 0 minus minus 1. 1 minus 1 times minus 3 is plus 3, so we get a 4 here. Still with me? Those who hadn't necessarily seen it. So now we take the quotient of 5 and 2. So it's 4 is fitting, so that's 2 times 2. And then 2 times 2 is 4, subtracted from 5. So that's 1. Aha, this is going to be our last row. 1 minus 2 times minus 1. So 1 plus 2 is 3. Minus 3 minus 2 times 4, so that's minus 8, that's minus 11. And that's our result. So from here we get that the inverse of 7 mod 26 is minus 11. So this gives that 7 inverse is congruent to minus 11 mod 26. And then it depends on your personal taste and what the exercise is like, whether you're okay having a negative number there or not. So you can write, and probably the one is 15 mod 26. Okay, we're not done yet. Now we know that this equation, so 7 middle 7s is equal to 9, coming to 9. Now you want to get rid of the 7, so we multiply by 7 inverse, so we multiply by minus 11 here. That means we also multiply by minus 11 here. And now here's me at the blackboard thinking about how to invert how to reduce minus 99 mod 26. Okay, so 26, then we have 52, and then we have 104, and so that's 5 more than 99. Okay, so what I have here is minus 99, that is the same as minus 5, and that's the same as plus 21. Mod 26. Now I said before, those of you who have done this before, you have to watch over me as a... Yep, what's... That's exactly the fear. I'm taking 104, I'm subtracting 99, that is very much plus 5. Thank you. Good. So now we have that S. Okay, this, if I multiply it by inverse of 7, we're getting S. So we have S is equal to 5. Which may or may not be what you calculated. Now we're getting back to this equation because we want to get R. We know, I mean, this is now back to linear algebra, and nice enough, this doesn't need another inversion because we have 1 times R there, so 1 times R plus 3 times S, so that's R plus 3 times 5. And that was same as -9 for 26. So now we're taking -15, and then we're getting that R is the same as -9 minus 15, so that's 24 minus 24, which is the same as +2, or 26. None of these steps was hard, and if you were using a computer, say you told Mathematica or Harry or whatever is your preferred computer algebra system to just solve this set of equations, mod 26, it would happily oblige. Now this thing can go totally wrong, because I'm asking you to invert mod 26, and I'm saying you can only invert something where the GCD is 1. I mean, if the GCD is not 1, you will get the GCD as such an expression. Say the GCD is 12, is 2 or 13. Then you have 2 times 2 is equal to whatever your integer was plus something times 26. Now 26 is even. This is even, so you can't ever get to a 1. I mean, if the GCD is 2, then both of these numbers are 2. So there are no x's and y's, so you couldn't get to 1. That means something which is an even number is not invertible, mod 26. So when I was making this exercise, I had to be very careful that all your numbers are invertible, because else this exercise is pretty frustrating. You can still sort of solve it. You can invert it mod 13 and then try, say you get an even number, you invert mod 13, then you try both choices. Either you assume it was the 0 mod 2 or 1 mod 2, but it is not like a 1 go. So note 26 is not prime. So inversion may fail. And then you can bootstrap So for instance, if the thing you have to invert is even, you can solve mod 13. And then try x and x plus 13. But this is not really elegant. This is not what you want. You can also brute force because it's just 26 possibilities. But it's not always going to work. So when you see something in an exam, it is pretty much clear that I have constructed in a way that it's solvable. If not, then Gustavo and I messed up. Probably, I mean, at least for this exercise, if you hit something which is not invertible, go back and recalculate. Okay, this was a quick recap of how inversion mod integers works. If you have not seen this, I do assume that you know this, so spend a moment on redoing that. We now have a break till 45.